One more. Okay, so recording has begun. Okay, so hopefully you see in front of you the notes I have for today's lesson 2.2b. We're really the most important concept for this class for the whole semester is going to be introduced, and that is instantaneous rate of change. So I don't have many problems on tap for this lesson, so the assignment for this lesson is fairly short. But I'm going to take some time up front to describe what the instantaneous rate of change is, which is also the derivative, which we'll be working with all semester long. Now, instantaneous rate of change evolves from a concept that you saw in the last lesson, 2.2a, and that is average rate of change. So I'm going to bring that back. Average rate of change. And an average rate of change applies to a given function on a given interval and here's a formula for it. So it's a difference of y values divided by the difference in the corresponding x values. So now I'm going to use this to tell you what instantaneous rate of change is. Now, instantaneous rate of change, like average rate of change, also applies to a given function, but whereas average rate of change deals with an interval of x values, so all x from here to here, instantaneous rate of change, as indicated by, as suggested by the name, applies at a particular instant, at one point. So we just have one point, which I'll call x naught, and the way we indicate it is with a prime, so f prime at the point x naught. So what we have here is it's defined in terms of an average rate of change so again, a difference of function values divided by the difference in those x values but in this case, we can simplify this down below. And just cancels those x's, so the denominator is just h. Right. But it's not simply this. I need to add a condition here. As h goes to 0. So you can think of h as so h, not think of it, it literally is, h is the width of this interval. So, and we think of h as being something small. So we figure out the rate of change on this interval of width h, but then what we do with this average rate of change is we let the width of the interval go to 0. someone admitted here. Okay, very good. Okay. Now, I want to explain what I mean by as h goes to 0, because I can't simply take this expression and set h equals 0. Can anyone tell me what goes wrong if I take this formula right here, this whole fraction, and simply set h equals 0? What would I get in that case? Be sure to unmute yourself.
It's undefined.
Yes. What is the actual expression you get that is undefined? Like, or can you, like, why would it be undefined?
Because the fraction would be over 0.
It is over 0, but what else? But what is the whole expression when you set h equals 0? Yes, you have 0 in the denominator, but what else?
Oh, would it completely cancel out because the 0 in the top would make it f of x minus f of x?
You do get 0 up top. So what you have is not just something over 0, you have 0 over 0. So now if I were to give a formal definition of what this means to let h go to 0, that would provide maybe mathematically rigorous, but I can also tell you that it would give you no illumination whatsoever as to what this actually means. So I'm not going to do that, but I'll give an informal explanation. We can't set h equal to 0 immediately. We can do it after simplifying whatever expression this is. So in other words, if I fill in a particular function f, like f of x equals x squared, which I will do in a little bit, then through algebraic manipulations, I can get something here where it is feasible to set h equals 0. So to explain what goes wrong if you don't simplify first, setting h equals 0 immediately gives 0 over 0, which is called an indeterminate form. Now, you would know from prior classes that dividing by 0 does not go well. But there's actually a distinction between, for instance, 1 over 0 and 0 over 0. They're both undefined, but what can happen is generally when you have something non-zero divided by 0, it's something that's becoming infinite. Like, for example, if a function 1 over x, if I let x go towards 0, 1 over x, so x is getting smaller. 1 over x is getting larger. It's going off to infinity. But 0 over 0, on the other hand, that would come from something like this. Anything is possible. So depending on the situation, 0 over 0 might be something that's going to infinity. It might be something that's tending towards an ordinary number. And that's actually what's going to be happening here. And I'll illustrate this in just a little bit. So think of it this way. If you're trying to determine an object's speed, what you can do is get its position at a certain time, and then take its position at another time, and then you take change in position divided by change in time. That tells you the object's speed, if it's going at a constant speed. But what if it's not? So then all you're doing is getting the average speed during that time. Now, if you want to know the instantaneous speed, so that's the speed at a particular instant, what you could do is try to estimate it better. Measure its position at 2 times that are very close together. The closer together they are, the more accurate your estimate of the speed will be. Instantaneous rate of change takes this concept to the extreme. We actually let that interval go all the way to 0 and see what we get. And I'm going to illustrate why that's would actually work. So as an example, I'll let f of x equal x squared, and I'm going to let x naught equal to 2. And I'm going to go ahead and compute this for different values of h. Okay. So in this case, that would be x naught is 2. Your function is x squared all over h. All right, so I'll just pick some small values of h and fill them in here. All right, so first I'll say h equals 1. So something that's not very small. So what we get is, so based on this notation here, this is f prime of 2. Actually, no, it's not. Only as h goes to 0. So what do I get for this when I set h equal to 1? So I get 3 squared minus 2 squared all over 1. So 9 minus 4 is 5. So I get 5. Let's let h get smaller. So 0.1. So that'd be 2.1 squared minus 2 squared over 0.1. So that's something that one would grind out in their calculator. Okay, which I'm doing off screen right now. And that would be 4.1. Let's let h get smaller still. 0.01, so I get 2.01 squared minus 2 squared over 0.01. All right, so that's 4.01. So what do you think is going to happen if I were to continue to let h get smaller and smaller? What would happen to these numbers?
They would continue to just get closer to 4.
Yes. Now, so let's take this to the extreme. Now, I cannot just set h equals 0 here. I would get 0 over 0. But okay. So then what happens is my fraction 2 plus h squared minus 4 all over h. So I can FOIL this out. So that would be 4 plus 4 plus 4h plus h squared. Oh, since I heard some background noise here, I can tell you that this week, someone did not have themselves muted. This week, 2 of my colleagues in the math department had situations in their class, online class, where someone was not muted and was engaging in a profane tirade. So something everybody has to be careful about. Okay. So what I can do now is simplify this. What can I simplify? What can I do with this? Anyone?
You would take the h out, and so it would be 4 plus h.
Before I can do that.
Oh, okay. Sorry.
Yeah, please back up. There's something else I have to do first. In the numerator, just focus on the numerator.
Yes, sir. The 4's cancel out.
Yes, that's what I was looking for. Okay. So we have 4h plus h squared. Okay, now up top, every term has an h in it. So, okay. And now you can see we have another cancellation, this time a multiplicative one. The h's will cancel. So we get 4 plus h. Now you can set h equal to 0 without having any division by zero concern or any indeterminate form. So that's why 4 is the instantaneous rate of change. So for f of x equals x squared, f prime of 2 is equal to 4. So, so what does this actually tell us? A couple of things. So the instantaneous rate of change of this function at this point is 4. What we also know is the tangent line to the graph of this function that's tangent at this point, x not equal 2. So it's a line that touches the graph at this point, but it doesn't cross the graph. It at that point, it has the same slope as the graph. But this line has a slope of 4. All right, so the instantaneous rate of change of a function at a point is also the slope of a tangent line at that point, which also means that at this point, has a slope of 4. Now, you know that f of x equals x squared, that is a parabola. That is its graph. So at different points, the curve has a different slope. But we know that at this point, this is the slope. So the instantaneous rate of change, we also know as the derivative. So the derivative of a given function at a given point is, so the formal definition, so it uses this notation, f prime, x naught. So it's this fraction that we've been dealing with. And how it's written rigorously is this. It is called the limit of this expression as h goes to 0. Now, what that means, as far as how you actually get this, is what I just described here. You cannot simply substitute h equals 0. So if you can substitute h equals 0, that is the limit. But in this case, you cannot, because you get 0 over 0. So for a given function, you figure out how to algebraically manipulate this expression, like what I did here, so that then you can set h equals 0, and then you get the derivative. So the derivative, another notation for a derivative that you might see is this notation, df dx. I mean, most of the time you'll see this notation, but it's also referred to this way. You've seen for dealing with a slope of a line, like delta y over delta x, and delta means change. This is the same kind of thing. It's a change in f divided by a change in x, but it's as the change in x goes to 0, and that's why the letter d is used instead of the Greek letter delta. So the derivative is synonymous with the terms I've given already: instantaneous rate of change, also slope of a tangent line. Which is also the slope of a curve at that point. Okay, so all of these mean the same thing. Now, here I showed how you could get the derivative from this definition for a specific function, x squared, at a specific point. But you're going to be computing derivatives of functions at points all semester long. Going through this process would be quite tedious. Now, one thing to keep in mind is although the derivative is defined to be a rate of change at a specific point, x naught, it's helpful to think of it as also being a function of x. So to show you what I mean by that, if I again let f of x equal, actually I'll make it something different. I'll choose x cubed. So here I'm not going to pick a specific x naught. I'm going to let x remain a variable. So f prime of x would be this fraction, x naught plus h, sorry, not x naught, just x plus h cubed minus x cubed all over h. And then we see what happens as h goes to 0. So same idea. It's just I'm just not setting a specific number here. So x is just x. So I could try working this out. And if I were to do that, there'd be a little more work involved because we're cubing instead of squaring. But what we would get from multiplying all this out would be x cubed plus 3hx squared plus 3h squared x plus h cubed. So then you can do the same kind of simplification as before. The x cubes will cancel, and then everything else has a at least one factor of h in here that would cancel with the h that's down below. So if I were to go through those simplifications, what I would get, so these terms are gone. I would have this one where I've canceled the h's. Then I have this one, where I've canceled one factor of h. And then I have this, where again, I've canceled one factor of h. But we are still taking h going to 0. So now we can set h equals 0. That's gone, and what's left is 3x squared. So what this tells me is at any point x, the derivative of x cubed is 3x squared. So that would be the slope of a tangent line at whatever x I plugged in. So we no longer have to plug in a specific point and work this out. We can work with whole functions at a time. So if I want the slope of x cubed at, say, x equal 5, I get this, and then I go ahead and plug in x equal 5. I don't have to plug it in back here. But the thing is, going through all this is still excessively tedious. Because even these functions, these are relatively simple. There are some very nasty functions that I could give that, so we're going through this would be incredibly painful, or you might not even be able to do it without using more advanced ideas that we wouldn't really even cover in this class. So going forward, we're not actually going to make use of this definition of a derivative directly. We'll learn what are called differentiation rules. So what that means is for a given type of function, here's how you take a derivative. What if it's a power of x or an exponential function that we'll see later, things like that. Or if a function is a sum of other functions, how do you take a derivative of that? What if it is a product? What if it's a quotient? So various rules you'll be learning later in this chapter for taking derivatives of functions much more easily than using the definition. But I wanted to let you know where these rules come from, what they actually represent, what the derivative actually means. Because there's no point in taking a derivative of a function if you don't even know how to interpret it. And that's really what today's lesson is about, is, first of all, what is an instantaneous rate of change? How do we define it? And also, how do we interpret it? So starting next week, so the next class on Monday, so lesson 2.3, is when we start getting into how you actually take a derivative of a given function. All right. Now, so now we're going to take a look at sample problems from this lesson. All right. So for example, here, it's important to pay attention to what information you're given about the function, so that you know what the function means and you know what its derivative means. So in this case, the function f represents velocity of a car, and u refers to time in hours. So now the way these questions will be described in Hawks often will be multiple choice. I'm not going to go through the various choices in here. Let's go over what the correct answer is. Now, so in this case, because f represents velocity, f prime is rate of change of velocity. So now we're going to see multiple choice questions. Well, again, it's not multiple choice right here, but in Hawks, questions like these about interpretation all semester long. These are probably the easiest points you can get. But I still see many students miss out on them. So one thing that I need to emphasize is, so literally emphasize it here. All right. So if a question is asking you, what does f prime represent? It is always a rate of change of whatever the function represents. F is velocity, therefore f prime is rate of change of velocity. It might be phrased in different ways, but again, but still boils down to it's a rate of change. Now, although it's next week, we're really getting to taking derivatives of functions. There's one very simple case that is covered right here. Here's a given function, f of x is x minus 1. Now, this function is a line. Now, I mentioned last time about average rate of change. If f represents a line, so it has a slope and this y-intercepts, its average rate of change is just a slope m. Now think about a line as opposed to any other kind of function. Is it always has a same rate of change. It's always the slope m. So it doesn't matter what interval you're dealing with, the average rate of change is m. But the derivative is obtained from taking an average rate of change over an interval that's getting smaller and smaller. Well, if the average rate of change is always m, then the instantaneous rate of change must also be m. So when you have a linear function like this, the derivative is simply the slope. So that's the simplest kind of function, or one of the simplest kinds, to take the derivative of. So what that means is, if your function represents a horizontal line, so the slope is 0. So if f is a function is simply a constant, its derivative is 0 because the slope is 0. So here we have a line, x minus 1. The slope is 1. So that would be the slope of its function, so it's also what the derivative is. Now, certain questions that you'll see ask for interpreting statements involving a function and its derivative. This is where you remember the derivative is a rate of change. So this statement saying that f, not its derivative, just plain old f, at this x value of minus 4 is equal to minus 505. So that's just the value of a function. By contrast, the derivative, what does derivative mean? The derivative is the instantaneous rate of change. It's the slope of a tangent line. It's also the slope of a curve. Those are three meanings. They're all different ways of describing the same thing. But it's important that you are aware of that for questions like these, that any of these things, instantaneous rate of change, slope, is referring to the derivative. So some of the other options, like if this is coming from a multiple choice question, you might be asking about this and saying that if a value of a function is, well, no, it's a derivative. So very important, don't get the function and a derivative mixed up. This is why you remember that the derivative is always referring to some kind of rate of change. Okay. All right, here we have a function of a specific meaning. F is total number of people that have a symptom, so sadly relevant for these times. And X is how many days has elapsed since the first case happened. So if we're saying that F of 10 is equal to 800, well, 10 refers to number of days since the first case. 800 is, look at the meaning of a function, total number of people that have the symptom. So that's all that statement is saying. Whereas if we have this statement, the derivative of a function after 10 days is equal to 6. So again, derivative is referring to a rate of change. Roughly what this means is that after 10 days have passed, the change per day, like how many new people are picking up the symptom each day, is 6. So this might be a situation where after 10 days, 800 people total have shown the symptom. But after 10 days, you have not many people picking up the symptom new. So maybe if the rate was higher before and it's slowing down. But these are the kind of key phrases you look for to realize, oh, it's talking about the derivative. Right. Here we have a function whose meaning is, okay, X is number of years since 1977. And we get a lot of questions like this where X refers to like some shifted unit of time. So for X referring to a given year, this is a number of strikeouts per game. Now, one thing I want to point out before getting into this question is a problem like this in a math class seems painfully contrived. Like, would one ever come across something like this, out in the wild, out in the real world, like where do functions like this come from? And that's something I can actually tell you, that such functions do come up in real world applications, but how they're obtained is, so what one could do is look at a whole lot of data. If you gather data on strikeouts per game, and then they try to model how that function behaves over time. Say if you want to determine, has the number of strikeouts per game, how has it changed over the years? Is it steady? Is there some clear trend of increase or decrease? So they could, for example, find the number of strikeouts per game for a specific year, like starting from 77, then again for 78, and have a whole bunch of data points. One data point for each year. And then they try to fit a function to that data. For like some of you may be familiar with least squares fitting that comes up in some science classes, or other methods to try to describe how the data is behaving using a relatively simple function such as this one. So what this would suggest is, because the slope here is positive, there's a clear trend of increasing strikeouts per game, at least since 1977. So there's a lot of data fitting like that to describe the data that one gathers. So not something how of that we don't get into in this class, but I just want to say these problems are not as contrived as they might appear. Okay, so here we have the value of f at 24. So what would that mean? So given the information here about what f of x is defined to be and also what x refers to, does anyone want to take a stab at this? So So f of 24, what would it represent?
It would be the number of strikeouts per game after 24 years from 1977.
Yeah, so 1977, and then add on 24 years. So you have a number of strikeouts in 2001. Now, what's done here is, like, this is what will happen in the question Hawks. It would require that you actually plug in x equal 24 into here and get a value, and that would be 6.65. So this is how many strikeouts per game there are during that year. So 24 years since 1977. By contrast, the derivative, well, this is a function that's just a line. So the derivative would simply be the slope of a line. So it would be so f prime at any point, not just x equal 24, but any point would be equal to 0.065. But as for what it means, well, since f refers to number of strikeouts per game, f prime is the rate of change in strikeouts per game. And again, in 2001, because x is 24. All right. So does anyone have any questions about the problems that I've shown here? Okay. We're doing pretty well on time. So there's one more thing I'd like to discuss. And while I'm doing that, someone disappearing. Okay. While I'm doing that, which I think still will not take up the whole rest of the time, if anyone thinks of any questions, then please share after. Okay. I want to make a comment about the relationship between average rate of change as opposed to instantaneous rate of change. Now, I've already mentioned one relationship, that the instantaneous rate of change, or derivative, is defined in terms of an average rate of change. We're taking average rate of change over a increasingly smaller interval, but there's more to it than that. I'm going to put this on a new page. But we have this, which is called the Indeterminate Theorem. I want to emphasize this is not something that will show up on any coursework. I'm using it to point out an interesting aspect of instantaneous and average rate of changes, which says the following. And I'm not going to state it completely rigorously, but the average rate of change of a given function on a given interval, like from A to B, is equal to the instantaneous rate of change of the same function at some point x equals c where c is between a and b. So another way to describe it using an equation is this expression, which is the average rate of change from A to B, is equal to the derivative at a specific point that falls somewhere between A and B. It doesn't say where it is, but it's somewhere in this range. Now, so one use of this idea of a notion that the average rate of change and the instantaneous rate of change coincide at a certain point is this. You can use this relationship between instantaneous and average rate of change to prove that someone has been speeding without actually observing it. All right, so suppose we have a car that's at a certain position. And let's just make this concrete and say that they're driving on I-59. So let's determine that their speed at that point, at that time, is 70 miles an hour. So they're fine. They're not observed to be speeding. And I'll put some units here. Let's say that T1 is in minutes. And we'll measure a position in miles. Okay. So there's one observation at a certain place, certain time, certain speed. Then at a second time, which is equal to, I'm going to make these numbers kind of extreme just for the illustration, but you get the idea. So 2 minutes later, they're observed at a second position, P2, and that is P1 plus 3 miles. Okay, so at these two times, T1, T2, the instantaneous rate of change is observed to be 70. So then we ask, between times T1 and T2. Well, so that would be the difference in position in miles divided by the difference in time. Now, I want the average speed in miles per hour, but what I'm going to get here is not in miles per hour. It's going to be miles per minute. But then I'm going to multiply that by 60 minutes per hour, just to make the units work out how I like. So what we get here is we'll go ahead and fill in all the numbers, or the numbers that are laid out here. Who can tell me what the average speed turns out to be?
Nine miles per hour.
Yes, it is 90 miles per hour because the difference in position is 3. The difference in times is 2 times 60, so we get 90 miles per hour. Okay. So this is a situation where at this point they're going 70, and then they crazily speed up over the next couple minutes, and then before we get to this point, then slow back down. So in fact, they had to be going in excess of 90 for most of that stretch, but slowing down to 70 just in time for the second observation here that happens 3 miles later, but only 2 minutes later. So I have a mean value theorem at some time between T1 and T2 they had to be going exactly 90, just because the average rate of change, average speed was 90 miles an hour. So at some point between these two observations, their speed had to hit that point. Now, realistically, it would have exceeded it also, but by how much we would not know. But it had to hit 90 in order for the average over that whole 3-mile, 2-minute stretch to be 90.
So would 90 be the instantaneous rate of change?
Only at some point between these two times.
Okay. Thank you.
Yeah, so we simply don't have enough information to say more than that. But the mean value theorem does give us that much. Now, I cannot imagine that cops would try to use this because it probably would not hold up in court. Start to mention calculus, and I think everybody involved's eyes would glaze over. What could probably happen is try to use this, a calculus literate defense lawyer could probably try to find a way to shoot it down. The mean value theorem actually has certain assumptions, which I did not take the time to state here. So one could claim that those assumptions do not hold. But still, it's a good way to highlight the relationship between instantaneous and average rate of change, and what kind of things can be reasonably be inferred from it. So this is just something a little extra, but I want to give you an idea of how this kind of information can be used. Okay. Now, we still have a good amount of time here. So does anyone have any questions either on what I presented here or whatever lessons you're working on? Do we have time? What do you got? I notice that just about everybody got the Chapter 1 review done. The next assignment is due tomorrow night. And in case there are any last-minute difficulties with those, I will have my office hour tomorrow at 9:30. Let's see what's in the chat. Yeah, all class meetings are posted in Canvas. Okay, what I will do is I will end the recording. So if you have any questions you want to ask individually, I will stick around. The rest of you are free to go.